So let's look now at the second half, the second part of transforming a graph. And we're still going to continue to look at reflections of a graph, but this time we're going to add compression and expansion both vertically and horizontally. So let's explore this a little further. Now we're going to look at reflections now in a coordinate axis, flipping it over either x or y axis. And we're going to compare the function given there of y equals negative root x with our basic function of y equals root x. And if you remember the points for y equals root x, it starts at 0, 0, over 1 up 1, over 4 up 2. Remember just putting in values for x that we can easily take the square root, over 9 up 3, and there's our basic function. There is the function y equals root x. So what happens if we put a negative in front of that? And we're going to do this with a table of values the first time. We're going to put the same x coordinates we put in before, 0, 1, 4, 9. And now we're going to take the square roots. And it's pretty easy to see what's going to happen here. When we put x equals 0, we'll get y equals 0. If we were to put x equals 1, and remember we're putting this into the equation, we're just doing this calculation in our head, square root of 1 negative will give us a negative 1, and all of those values will become negative, negative 2, negative 3. So what does this new graph look like? Well, it still starts at 0, 0. Now instead of being 1 over 1 up, we're going 1 over 1 down. 4 over 2 down, 4 negative 2, and 9 negative 3. And there is our graph. Now what we can see is this graph has been taken and it's been flipped over the x-axis. And the only difference there is that negative. Well, let's keep that in mind as we do one more exploration. Again, start with our basic graph of a square root function. We're always going to compare to our most basic graph. There's our graph y equals root x. Same thing we did before, x and y, plug in those x coordinates that are easy to take the square root of. Now if we put 0 in there, we'll still get 0. Here's our first problem. If we put y equals the square root of negative 1, we can't take that square root. So we actually have to adjust our domain values. We don't want to put 1 in now, but negative 1. So if we put negative 1 under the square root, how that's going to look is we'll have negative 1, which would make this square root of 1, which of course would just give us 1. Same thing with 4 and 9. Instead of positive, make them negative. Square root of negative 4 negative is going to make it positive 4. We'll make this a 2, and it's pretty easy to see that we get 3 there. So what does this graph look like? Well, we still start at 0, 0, over 1. This time, though, to the left, negative 1, 1, negative 4, 2, negative 9, 3, and there's our picture. And what does it look like has happened to this picture? Well, it's been taken and it's been reflected across. Remember when we're doing a reflection, we can consider that there is a mirror right there, a reflection across the y-axis. And again, the only thing that's different is that negative sign. So we can now extend this to any function. If we have a negative outside the function, like in the first step here, we know the negative is going to cause a reflection. And the negative outside the function, if we look back to the example we did, outside the function was a flipping or a reflection across the x-axis. A reflection across our x-axis, and we can generalize that for any function. Really, what have we done? We have taken all the y values and we've just multiplied the original y value by -1. That causes the reflection across the x-axis to change all the y values by multiplying by -1. Well, what happens if it was inside the function, like this example? Well, that inside the function was a reflection across the y-axis. That's how we could generalize this. Inside the function is a reflection across the y-axis. And if we look at our numbers, what we really just did is we multiplied the original x value by -1. Just changing the x and y values. That's how we can do a reflection across our axis. So let's apply this. Here's our original function f of x. We want to describe the transformation as well. We want to map the general coordinates of the image points. Well, it's pretty easy to see here. We have a negative inside the function. Inside the function is going to tell us this is a reflection. And we just have to be careful if it's inside. It's across then the y-axis. There's our description of this transformation. And if we wanted to now apply this to the graph, well, that's going to take all of the x values and make them negative. So if we were mapping the general coordinates, our original coordinates were x, y. Our new coordinates are we take the original x and make it negative of what it was before, just reflect it. So let's look at a point here. Let's consider this coordinate right here. And this coordinate is at -7 and 3. If we were to reflect that, we would put that at +7 and 3. This point would get reflected to that new coordinate. It's just moved across the axis. Now we can take this coordinate, we can actually walk these if we want to. It is now 2 away, 1, 2 away in this direction, so we'll just have to put it 2 away in the other direction, just reflection. If we look at our coordinates down below here, we just are originally at 4, -2, so we'll be at -4, 2, like so, and we got one last point here. It's originally at 8, -2, so we'll be at -8, 2. And there are the points that have been mapped out. They've been reflected, which means now we can just connect the dots, connect our points together with a nice smooth straight line, and there is our reflected function, a reflection across the y-axis. Well, let's try another type of transformation. Let's look at expansions and compressions. And we're going to do an expansion or compression. Again, we're going to use the radical function, our basic graph of y equals √x, and we're going to compare to see what happens to this basic graph if we were to put numbers outside the function. And for this one, I do want to just put the original points in so we're clear. We're at 0, 0, 1, 1, 4, 2, 9, 3. So when we want to do this now, we want to do a table of values for the next function. This time we're going to put a 2 in front of the square root. Well, if we put the same x values in, 0, 1, 4, 9, we can compare to those values. If we put 0 in there, it's not going to matter, 0. If we put 1 in here, make this a 1. Square root of 1 is 1 times 2. This is going to make this 2. If we were to make this a 4, square root of 4 is 2 times 2 is 4. And if we were to make this a 9, square root of 9 is 3 times 2 puts us at 6. And you can probably already see a pattern, but let's put those points on the graph in red. We're at 0, 0, 1, 2, 4, 4, and 9, and 6. So what have we done to this graph? We can see that it's actually increased in size. Now that increase we call an expansion. We've expanded the values, and notice the expansion changes the y coordinates. We're expanding this in the y direction or the vertical direction. Well, let's try it one more time. If we put a fraction in, if we put 1/2, use the same x coordinates and solve these values. 0 stays the same. We put 1 in here. Square root of 1 is 1. That's going to put us at 1/2. If we put 4 in here, square root of 4 is 2. Times 1/2 is 1. And if we put 9 in here, we get 3. Half of that is, and we'll just use it as an improper fraction, 3/2. Well, let's plot those points. And again, you probably can already see a pattern here. 0, 0, 1.5, 4 and 1, 9 and 1.5, or 3/2. And look what happened to our graph. Now it's been squished. It's been compressed. It's like someone's come along and sat on that graph. And again, compressed in the y direction. It's as if someone has come along and pulled this graph down or pushed it up, compressed or expanded. So let's generalize this for any function. When we have an a value in front of the function, tells us that it is vertical. That's our first piece. X, Y. Vertical meaning the y direction. If it's greater than 1, just like our first example, that was an expansion. And we're vertically expanding this by a factor. And let's have a look back and see. If we look at our graph, when we put the number 2 in, all of our y values doubled. When we put the number 1/2 in, all the y values got cut in half. So the expansion factor is the absolute value of a. If a is 2, it's doubled. If it's 3, it's tripled, etc. So what if a is less than 1? We still have vertical because it's outside the function. This time, though, it's a compression because we're sitting on that function, making it smaller by a factor of a as well. Whatever that value of a. If it's a fraction, it's a compression. If it's not a fraction, it's an expansion. Well, let's put it into practice. Here's our function. We have a 1/3 in front of the function, which tells us right away this is a vertical. Because it's a fraction, it's a compression. And it's a vertical compression by a factor of 1/3. And all of the y values get multiplied by 1/3 or divided by 3. So take a second, pause the video, and see if you can actually graph this new transformed function. So there's the transformation of the points. All the y values have been divided by 3. Be careful when you get down to -8. Dividing it by 3 puts it at -2/3. And once you have your points, all you have to do is draw a straight line between them. And there is our new transformed function. All the y values have been divided by 3 or multiplied by 1/3. So if we were mapping these general coordinates, originally points were at x, y. Now we've taken all the x coordinates, keep them the same, and take all the y values and multiply them by 1/3. Well, let's look at one last transformation, this time in the horizontal direction. And the horizontal direction, we're going to now compare to a function that we do know, the quadratic function, that parabola. So sketch yourself a parabola quickly there. And once you have your sketch, let's put the table of values in for the original parabola of -2, -1, 0, 1, 2, because we're going to use these values to compare our new transformed function. What happens if we have a number inside that squared function? Well, let's do our table of values first time, and hopefully never again. X and Y, so let's put the same X values, -2, -1, 0, 1, and 2. And what is that going to do to our function? Well, if we put -2 into our function, let's do one calculation first to show what we're doing here. 2 times -2 all squared is, of course, -4 squared, which is 16. So we get a value of 16. If we put -1 in there, we'll get -2. Squaring that, we'll get 4. 0 doesn't change, and we get a pattern like so. So if we were to plot these points on the graph, we're still at 0, 0. Now we're at 1, 4, -1, 4, and the others are beyond the graph. So we get a graph that looks like so. And what's happened to that graph? Well, it looks like someone has taken this black graph and squeezed it. Remember, we're now talking about the x direction horizontally. We have taken this graph and we have now compressed this graph. And what have we done to those values by compressing them? Well, we have made that graph skinnier in the x direction. It's like someone has pushed on that from either side. Well, let's try with 1/2 in there. Same thing, same points. -2, -1, 0, 1, 2. If we use those values, and again, let's do one calculation to show what we're doing here. It's 1/2 multiplied by -2, and the whole thing is squared. This would become 1, or -1 squared, which would make this 1. So at -2, we would be at 1. We put 1 in there, we're going to be, quite small here, 1/4. 0 stays the same, 1/4, and 1. So if we were plotting this point, and these graphs are a little harder to plot, 1/4 gets squeezed in there. 2, we're at 1. And what I'm going to do is I'm going to add one other coordinate to make it more easy to see. Let's put 4 in there. If we put 4 in there, we get 2 squared, which would put us at 4. And we'll get a better idea of what this graph is. And there it is. Still that parabola, only this time it's like someone has come along and taken the original black graph and not squeezed it, compressed it, but now pulled on it on both sides and horizontally expanded that graph. So in the horizontal direction, we would consider this an expansion. Remember, we're only looking in the x direction for that expansion or compression when we talk horizontally. So let's look at these numbers, and actually this time, because we're changing in the x direction, we want to see how does the x value change given a specific y value. And let's look at the y value of y equals 4. Y equals 4 occurs in all three of these, and we want to see what happens to the x value when we put a number inside the function. Well, let's look at this x coordinate. If we went from the black to the red, the x coordinate got cut in half. It's like we took the original 2 and we multiplied it now by a half, which gave us 1. In the green coordinates, we took the original x coordinate of 2 and multiplied it now by 2 to give us 4. What we want to notice here, though, is the comparison between the number we're multiplying and the original value inside the function. And if you look at those numbers, you'll see If it's inside its 2, we multiply by a half. Inside a half, we multiply by 2. And we're going to use that when we define our function here because it's that reciprocal relationship. So inside the function, b is going to tell us we have a horizontal compression. We squeeze that graph, and it's a horizontal compression, but this time it's by a factor of not just the number, but the reciprocal of that number. If it was 2, we multiplied by a half. If it was a half, we multiplied by 2. So b, if it's greater than 1, it's a horizontal compression by 1 over b. If it's less than 1, we have a horizontal, not compression this time, but expansion by a factor. It's still the reciprocal, 1 over b, and again, we want the absolute value. So whatever that value is inside the function, we're always going to multiply the x values by the reciprocal. So let's use this. Here's our graph, f of x. We have a 2 inside the function. We first want to describe this transformation, and as soon as we see that it's inside the function, we right away know that it's a horizontal, and now we have to decide, is it compression or expansion? It's greater than 1, so it must be a horizontal compression, and this time it's by a factor of 1/2, the reciprocal of that number. If we were mapping these coordinates, our original x, y values, what we would do is we would take our original x and divide it by 2, keeping y the same. So pause the video and now see if you can graph this transformed function following that mapped coordinate. So there's your points, x value cut in half, and now we just take those points, connect them with a nice straight line, and we have our new transformed function, horizontally compressed by a factor of a half, like someone's come along and squeezed it to compress it on each side. And we're going to look at that in more detail and combine them together in class.